Okay, so we're going to actually look over some of these types of oxidation reduction reactions and try to identify them. That's something you're going to need to be able to do, like combination reactions. They're coming together. Decomposition, they're breaking apart. Okay, combustion. Combustion, you can see, is actually can be considered combination as well, right? Because you have these two things coming together. These two things coming together. So not always, but sometimes you can consider that a combination reaction. But it's also a combustion reaction. Sometimes you identify things to be more than one type of reaction. Okay, but this would be an oxidation reduction, combustion reaction, or a combination reaction. Okay, this is a displacement reaction. So where one thing displaces another thing in the reaction. So here we have A, and it's going to displace B, and you're going to end up with AC plus B. So hydrogen displacement is a process of producing hydrogen gas from water. So strontium would do that. Strontium plus water would replace the hydrogen. Then you would form a strontium hydroxide, okay, plus hydrogen gas. Now that process there with strontium happens with most of these first metals on the periodic table, the alkali metals. Lithium would do that. Sodium would do that. Sodium metal. Okay. Here we have a metal displacement. So instead of producing hydrogen gas, we're just displacing a metal. So here we have magnesium. It's pure magnesium. And it's going to displace the titanium here and form magnesium chloride, and titanium will come out. Okay. And here is a halogen displacement reaction. Halogen displacement happens when you have two halogens. One of them is in a compound, the other one is pure. Okay, just the halogen all by itself. This chlorine is going to displace, the bromine. And so you get bromine out, and the chlorine goes back in. And so there's an activity series that we're going to look at for halogens that will describe that a little better. So these are displacement reactions, when something is displaced by another. We consider these to be considered single displacement reactions. Okay? And also with hydrogen displacement, you often get that if you're reacting a metal with an acid. It will displace the hydrogen of the acid and produce hydrogen gas. Okay, so here's an activity series for metals, different metals. You can see that. And you can see a lot of metals will react with hydrogen. As you can see on this activity series, they will, because they're above it, they will react with hydrogen or acids. So we can consider that H plus or H as an acid. So this is an acid. And all these metals above it would react with it. And they would allow for hydrogen displacement and produce H2 as the metal. Okay? But these metals down here wouldn't. So if you react copper or silver or mercury or platinum or gold with an acid, it's actually not going to react. They're not going to react with acids to displace hydrogen. But all these other ones here would. These all would. Okay? So that's kind of how we can read this chart. And here are some examples. So this is a hydrogen displacement reactions, but for water, in water. So what acids would displace hydrogen in the presence of water? So here we can see any of these ones: lithium, potassium, barium, calcium, sodium. Okay, like I said, that very first column there. Those guys are going to displace hydrogen in the presence of water and do a single displacement reaction, okay, to produce hydrogen gas, H2 gas. So this is going to come off as a gas. It's going to bubble off. And you're left with the metal hydroxide after that. Okay? So this activity series is telling you this one reacts with cold water to produce H2. This one reacts with steam, so it needs to be at a high temperature for it to displace the H2. This one doesn't react with water. These ones only react with acids, okay, to produce H2. So cobalt, nickel, tin, lead, Those ones wouldn't. So here you can see lead plus water does not produce lead hydroxide plus H2, which, you know, that's a good thing because there's all kinds of lead pipes around, right? And you don't want to be producing a lot of hydrogen gas in the lead pipes, and it's corroding the pipe or whatever. So that would not happen. But this one, calcium plus water. So if it's pure calcium, just calcium all by itself, and you put it in the presence of water, it's going to create hydrogen gas. Okay. Here's the activity series for halogens. Okay. So here you can see that bromine at a -1 charge goes to a 0 charge. What do we call that? Oxidation or reduction for bromine. Bromine was, did it lose or gain? Okay. Bromine lost electrons. Okay. So this is oxidation. Okay. Bromine was oxidized. Okay. Chlorine was reduced, right? So chlorine was reduced. Bromine was oxidized. So chlorine is a what? Agent. If it was reduced. Okay, it's the oxidizing agent. And bromine is the reducing agent. Okay, so that's how we would identify this. Okay, so when we look at the activity series here, chlorine is an oxidizing agent. Chlorine is a stronger oxidizing agent than bromine. And because it's a stronger oxidizing agent than bromine, okay, it causes the oxidation of bromine. But can bromine cause the oxidation of chlorine? No. Okay. Can iodine cause the oxidation of bromine? No, and that's what we see here. Okay. Iodine cannot cause the oxidation of bromine. So you're only going one way in this activity series, starting with fluorine. Okay, chlorine could act as the reducing agent of F2, but F2 could not reduce chlorine. Okay, so that's how that would work. Okay, with the halogens. Okay, here's another type of oxidation reduction reaction that we would want to be able to identify, and that's a disproportionation reaction. Okay, so this happens when you have the same element that takes on different oxidation states. So here we see chlorine at an oxidation state of 0. But when we look at what it becomes, okay, here, what happened to chlorine? Was it oxidized or reduced? Oxidized. It lost electrons. What about here? It was reduced. So we have oxidation reduction happening on the same molecule. Okay, chlorine broke up into 2 chlorines. One of them got oxidized, the other one got reduced. This one got oxidized and with this oxygen, okay? And here it just became chlorine minus. And so we have a disproportionation reaction because of that. So if ever you see one thing over here becoming 2 things over here, it's possible that that's a disproportionation reaction because you would have to identify the oxidation states of the elements on the other side to identify whether they're at the same oxidation state or not.
What about the agents? Reducing agent.
So on this one, basically the chlorine is both. Because one of the chlorines is the oxidizing agent, one of them is the reducing agent. Okay? Because the oxygen and the hydrogens didn't do anything. They didn't change oxidation state. Okay? This has a -2, this has a +1. Over here it has a -2, and over hydrogen has a +1. So they didn't change oxidation states. So they didn't do anything. So chlorine here and here are the things that were oxidized and reduced. And so that's how you would have to describe it. Okay, so let's try to classify these. So N2O becoming N2 and O2. What kind of reaction would you classify that as? What's that? Okay, now if I was going that way, yeah, because I would be reacting it with oxygen. But my product is oxygen instead of a reactant. Decomposition. So this is decomposing, right? It's this, and it's becoming its constituent elements. Okay? So that'll be a decomposition. Okay, how about the next one?
Combination.
Good. So we're taking two things, we're reacting them together, and we're forming one thing over there. That's a combination reaction. Okay? That'd be a combination. Okay, how about this one? Okay.
And that would be lead displacement?
Well, the lead was displaced, so I guess you could describe it as lead displacement. Or metal displacement is what we would mostly describe it as. If it was a hydrogen that was being displaced, if this was a hydrogen instead of a lead and the hydrogen was nitric acid, the nickel could displace the hydrogen. That would be hydrogen displacement, but this would be metal displacement. Okay? How about that one? Nope, not. Okay, this is the clue. How many nitrogens do I have over here? Okay. And those two nitrogens, do they go to the same thing or to different things? What's that? Two different things, right? Okay. Now, what is the oxidation number of this nitrogen? Okay, let's review that. -2 for the oxygens, right? That's a constant, so we can trust it. So that's -4 overall for the oxygens. So that means that the nitrogen must have what state? +4. Right? Okay. What is the oxidation number of the nitrogen here? Is it still +4? Can't be. -2, that's -4. This is +1 for hydrogen, so the nitrogen is what? +3, right? Okay?
It doesn't matter that there's two nitrogens on the left side?
What do you mean?
Like the two.
Oh, we're not worrying about the balance.
Okay.
All we're worrying about is the oxidation number of that. Okay? So forget about the balance right now. That's not what we're worried about. All we care about is what is the oxidation state of the nitrogen, and does it change oxidation state? Now, if we are following the exact number of electrons, then the balance is going to be important because we're going to want to see where those electrons go. But if I'm just trying to identify the oxidation number, I don't worry about the coefficients. Okay? All right, so we have -6. This is +1. So what is the oxidation state of the nitrogen in the HNO3? +5. Okay, you guys struggling with that? Should we practice it? Think so? I think so. Okay, we'll practice it. So, do you see how this nitrogen and this nitrogen are at different oxidation states? This was at +4, right? Here, what did it do? Did it lose or gain? Okay, so
Okay.
0, plus 4, plus 3, plus 2, plus 1, 1, 2, 3, negative, negative, negative. Okay, so to gain electrons, I go this way, right? I'm becoming more and more negative. Plus 5. Okay, so this way I'm gaining electrons. If I go this way, I'm doing what? Losing electrons. So from plus 4 to plus 3, did I gain or lose? I gained electrons. That is called reduction. What happened when I went to a plus 5 right here? I lost. That is called oxidation, right? So we have reduction and we have oxidation. What kind of reaction is this? Disproportion. Okay? That's right. So this nitrogen was oxidized and reduced. So that's a disproportionation reaction. All right. So before we get into stoichiometry, which I love, okay, let's go ahead and practice some oxidation numbers. Okay. Okay, did everybody get one? Okay, so give the oxidation number of all the elements in the following molecules and ions. Okay, so go ahead. We'll start to work those out and we'll practice them in a few minutes. Okay, let's see really quickly how you're doing on this first line. Okay. So oxygen is -2, right? We can trust that. So the sulfur here would have what oxidation state? +2. Okay. Okay. So over here we have -2 for oxygen. Whoops. -2. That's -4 because I have 2 oxygens overall that the oxygens are donating. But if the question was, what is the oxidation state of oxygen? You would say -2, not -4. Okay? -4 is just telling me how many I have on that side of the compound. Okay? So the sulfur has what oxidation state in this one? +4. Okay? Because it has to balance those -4 charges from the oxygens. Okay? -2, -6. So this sulfur has what oxidation state? +6. -2, -6. But look at this. It's 2 minus, right? So that means I have -6 minus 2 that I have to balance. So I only have to balance -4 charges, right? Because I have 2 left over. So what is the charge on the sulfur? +4. Sure. So if I have +4 charges here, and I balance 4 of the -6 charges, how many are left over? -2. Okay? So I have to have those left over when I'm trying to figure out what the oxidation state is.
So the 2 minus and the -2, can you explain that for maybe that's the +4? I'm not understanding.
The +4? Okay. So I found out that I have -6 charges on that side of the compound. Okay, you okay with that? Okay, because each oxygen has -2. -2 times 3 is -6, right? So this means that I have a charge of -2 on the entire molecule. So that means there's 2 extra electrons that are unbalanced. So when I balance the -6 charges, I have to leave 2 of them unbalanced. So that means only 4 of the charges get balanced. So that's why it's a +4 that balances the other side and leaves 2 left. Okay now? Okay, this is -2. Goodness. Okay, we have -2, that's -8. So the sulfur +6 because we have a -2 charge left over. Okay? It's +6. All right, now try the next ones. Okay, let's look at these next ones. Okay, so ClO2, we have for this first one, we have -2 on the oxygen, but that's times 2, so it's -4. So the chlorine over here has what oxidation number? It's 4, right? Good. Okay. Here we only have one oxygen. It's -2. But what do we have? A -1 charge. So that means the oxidation number of this chlorine is what? +1. Okay? Because it's only balancing one of the negative charges, not both of them. So we have a -1 charge left over. -2, -4. What's the chlorine? +3. -2, -6. What's the chlorine? +5. -2, -8. What's the chlorine? +7. Okay? So do you see the difference between chlorate, hypochlorate, I'm sorry, not hypochlorate, perchlorate, chlorate, perchlorate, chlorite, and hypochlorite? It's the oxidation state of the chlorine. The number of oxygens is changing, but what happens to the charge? The charge remains the same, right? Because it's the chlorine that is changing oxidation state, and that's why it's not affecting the charge.
Shouldn't it be +7?
That is a +7.
Oh, okay.
You can't tell that's a +7? Just kidding. Yes, it should be +7. Okay. All right. Okay. Make sure you try those next ones. Okay, let's check to make sure you're getting these nitrogen ones right. What's the oxidation number of this nitrogen? +1.
Well, for 1, right? If you were wrong,
So
it was-
that's how
Yeah,
we,
yeah,
good,
yeah,
okay.
yeah.
So that's how you have to describe it. You can't tell me it's +2. It has to be for this individual nitrogen. For an individual nitrogen, what is the oxidation number? +1. Okay? So we have -2 for the oxygen. So that means that's +2 overall. So each nitrogen has a +1 oxidation state. Okay? So that's how you have to describe it. What about for the next one? +2. Good. And if you need me to show you why, then let me. Okay? But if you got it right, good. How about the next one? +4. Next. +4 also. So it's +8 overall, but there's 2 of them, right? So that means each individual nitrogen has a +4 oxidation number. So that's how you describe it. Okay? So +8 might be an answer choice. Don't choose that one. That's not the answer. What is the oxidation number of the nitrogen in this molecule? +4. It's plus 4. Okay? Okay. How about the next one? Good. Plus 5. How about the next one? Plus 3, right? So we have negative 4, but 1's left over. 1 is unbalanced. That means the nitrogen has a plus 3. How about the next one? Plus 5. Good. Because we have 6, 1's left over, so it's plus 5. Okay. Does anybody need me to go over that with anyone? Yes, ma'am. This one right here? Great. So we have negative 2 for the oxygen, right? So there's 2 of them, so that's negative 4, right? Charges from the oxygens. And there's 1 unbalanced charge. There's a negative 1 charge on the entire molecule. So that means that the nitrogen's at a positive 3 to leave 1 charge left. Okay, any others from that list?
Can you explain like the N2O4 and N2O5, whichever one?
Sure. Okay. So for N2O4, we have negative 2 for the oxygens, right? That's negative 8 overall. So if you take, that means I have to have plus 8 on the other side. That means each individual nitrogen, if I divide 8 by 2, is 4. So it's plus 4 for those nitrogens. Okay. For the N2O5, I have negative 2 times 5, which gives me a negative 10 overall. So I have to have a plus 10 on the other side. And if I divide plus 10 by 2, that means each nitrogen has a plus 5 charge on it. Okay?
What if the 2 was in front of that N? Wouldn't that
What do you
still
mean?
mean we still have 2 nitrogens? Like if the 2 was in front of the N?
Because we're not looking at how many N2O4s we have. We're just looking at what is the oxidation state of the nitrogen in an individual N2O4 molecule. There's only 2 of them in one molecule. That's what we're looking at, not at coefficients. So if we had a 2 right here, we don't care about that. That's not how we're describing these. We're just describing it simply as what is the charge of this nitrogen in this molecule. It has a plus 5. Okay? Okay? What's the oxidation state of sulfur here? Minus 2, right? Because hydrogen, what do we know about hydrogen? Positive 1, right? Plus 1. So that's plus 2 over here. So this is negative 2. What about a sulfur all by itself? It would be at 0. Okay? Anything all by itself would have a 0 oxidation state. Okay? If it was S2 minus, that's different, right? That's an ion that's charged. But any element all by itself, and this wouldn't actually be all by itself. It'd usually be something like S4 or something like that. Okay? But anyways, when it's all by itself, the oxidation state is 0. O2, 0. H2, 0. Sodium, metal, all by itself, 0. Potassium metal, all by itself, 0. Okay? So that's how you would describe it. It hasn't become anything that's in its natural state is always at an oxidation state of 0. If you saw S2, it would be 0.
Doesn't matter how many you have, it's still just 0.
Yes, if it's all by itself and it's not charged. If there's no charge on it,
But
then
like
it's
that
0.
S2 minus is going to have
That's going to have negative 2. Yeah, it tells you what its charge is right there. It's oxidation state. I have a negative 2 charge. Okay? So, what about this sulfur? Plus 6. Because each oxygen is negative 2. Negative 2 times 4 is negative 8. We have 2 hydrogens that balance 2 of those negative 8s. And what's left over? Plus 6. Okay? This one's 2, negative, right? What about E? It's, I'm sorry, it's negative. Negative what? Negative 2, because this hydrogen has a +1 charge, right? And it's only balancing one of the negative charges, so I have one left over. So it has, the sulfur is at a -2 oxidation state.
So the negative oxidation number, you still minus that one off, so it's -1.
The sulfur, because it's at a -2, that's why we have one left over, because we only have one hydrogen. If we had had 2 hydrogens, which would be this, see that it's still, well, I'm sorry. So this hydrogen has, these hydrogens have a +1, right? This still has a -2 for that sulfur. Okay? And it's the same thing here, +1, -2. It's just that I've lost a hydrogen between here and here. But it didn't change the oxidation state of the sulfur. But the charge of the molecule changed. Now it's at a -1 charge because I lost a hydrogen. Okay? SO2. Sulfur there. What is it? +4. Good. G. SO3. +6. There you go. Okay, that's right. Okay, let's look at these. The oxidation number of phosphorus in each of the following. HPO3. Good. +5. How about the next one? What is it? +1. Because I only have 4 negative charges. I have 3 hydrogens to balance 3 of those. So the phosphorus must have a +1 oxidation state to be able to balance the other electron. Okay? C.
+3.
Okay, so we have yep. Okay, +3. D.
+5.
Good. 14. Good. +5. It's 20. 15. +5. Okay, that's right. So 5 +1 +5 +1 +3 +5 +5 and +5. Okay? Does anybody need? Yes.
Just to clarify, if it's asking for the oxidation number on one of those where it has like a 2-, like say K, MO, if they were just asking for the oxidation
Right here.
something like that,
For
would it still be -2 then, or
the oxidation, let's see, 8. No, there's only one of them. So if you're asking about the oxygen, it'd be -2. What's the oxidation state of an oxygen here? It's -2.
okay? That's what I was. That's right.
Okay, but what is the oxidation state of this? It would be +6. Right. Okay, does anybody need me to go over any of these? Are you getting those numbers? If you're not, let me help you. We're okay? All right, so let's look at this last page. This last section, excuse me. Okay, for A, what is the oxidation number of CS? 1. +1. Good. What is it for B? What is it for B?
+4.
Okay, -6. Yep, +4. Because what is the oxidation number of a chlorine? -1 in this case. Okay? And that gives us -6 minus 2. That's -4. So we balance it with a +4. Iodine. Or, I'm sorry, the calcium. Okay, +2. Tin. What's this one? Plus 2. Okay. Al? Plus 3. Okay. Okay. CLF3? Okay. -6. Okay, good. Plus 3. Antimony? Plus 5. Titanium? Plus 4. Good. P4? 0. Excellent. Okay. We already did K. What was that? Plus 6. Manganese? Platinum? Plus, not plus 6. Plus 2. Okay. O2? 0. O3? Okay. Keep that at 0. Okay. Any questions on that? All right. All right, let's talk now about stoichiometry. Okay? And stoichiometry is kind of the epitome of chemistry, I would say. It's kind of the, if there's something you're going to learn about chemistry, it should be stoichiometry, because stoichiometry allows you to determine how much of a reactant you would need to use in order to create so much product. It gives you the mathematical tool to be able to predict outcomes or to understand how much of something you need to set up a chemical reaction. Okay, so it's really an important part of chemistry. So let's look at a simple, basic chemical reaction like this one. Okay, so I want to use this chemical reaction, and I want to decide if I have 2 moles of H2, how many moles of O2 will react with it, and how many moles of H2O will be produced. So I'm starting with 2 moles of hydrogen gas. Any thoughts on how I could answer that? What's that? Say it, I'm sorry. You guys did have a lot of thoughts. I just couldn't hear them all.
1 mole will react with the H2.
1 mole of what? O2? Okay. Why? I agree with that.
Because of the product.
So why 2 mole or 1 mole of oxygen? I'm starting with 2 moles of hydrogen. Why is it that 1 mole of oxygen will react with it? Because I only have 1 oxygen over here? Okay. That's a pretty good thought. Okay, that's true. Okay. But there's a better way. What if I had this? Let's try this one. Now what is it? Whoops, that's not even what I want. Right? That's impossible, Mr. Crandall. Okay, so let's try this. Now what is it? 2 moles of N2. How many moles of H2 do I need? What is it? Okay, so that one's not as obvious. Well, we could make it a lot more obvious. What do you think we could do to make it more obvious? What's wrong with these chemical reactions that I've shown you, both of them? They're not balanced. They're not balanced, right? So let's go ahead and balance it. That's going to be a lot more clear, okay? So if I need 2 oxygens over here, right? So I'm going to put a 2 here. Once I can write again. And that's going to cause me to have 4 hydrogens, so I need 4 over here. Okay. Now is it really clear why I need 1 mole of oxygen with 2 moles of hydrogen? Okay. But the other question is, how much water did I produce? How many moles of water?
2.
I produced 2 moles of water. The chemical equation is telling me exactly the outcomes, or what I need in the beginning, how much I need of everything. For every 2 hydrogen molecules, I need how many oxygen molecules? 1. And I'm going to produce how many water molecules? 2. So the balanced chemical equation gives me that information. It makes it very clear, very obvious. But when it's unbalanced, is it really clear or obvious? It's not, because I don't know the ratios yet. So let's go ahead and balance it. So now, if I have 2 moles of nitrogen, how many moles of hydrogen are going to react with that? 6, right? 6 moles, because 3 moles of hydrogen are going to react with every 1 mole of nitrogen. So that means if I have 2 moles, it's going to be 6 moles of this. Well, then how much NH3 would be produced? For every 1 mole of nitrogen, I produce how many NH3s? 2. So if I have 2 moles of N2, how many moles of NH3 do I produce? 4. Okay? So the chemical equation is telling me the ratios. It's helping me see the outcomes. Okay? And it is not doing it in gram amounts. Right? These coefficients don't stand for grams. 1 gram of N2 plus 3 grams of H2 is going to produce 2 grams of NH3. Does that make any sense? That makes absolutely no sense, right? Because I can't have 3 grams. This would be 4 grams. That would have to be 4 grams over here. That's not making any sense. Okay? So, because mass has to be conserved, right? The mass from this side to this side has to be the same. So, these coefficients don't represent the gram amounts. They represent the mole amounts. And when I have my chemical reaction in the mole amounts, I can visualize how much product I need, how much product I'm going to form from this amount of reactant. Okay? It's jazzy. Okay, so let's go ahead and take a different type of question. Okay, what if you have 0.8 moles of H2? Now it's a little less clear to see exactly how they're going to react, right? Because it's not whole numbers and, okay? But what is the same about it is the ratios. Still, if I have 2 of these, I only need 1 of these. So basically, half of this amount is what I need, right? So 0.8, I would need 0.4. Okay? And how much would I make over here? I would make the same number of moles over here as I started with of hydrogen, right? 0.8. So 0.8 moles of hydrogen gas plus 0.4 moles of oxygen gas will produce 0.8 moles of H2O. Okay? Now, there's another way to do this. We use the coefficients as conversion factors. I am starting with 0.8 moles of H2. And I want to know how much oxygen will react with that. So I'm going to say moles of oxygen. That's what I want to get to, right? What am I getting rid of? Moles of H2. According to your balanced chemical equation, what number would I put on top for this conversion factor? 1. What number would I put on the bottom? So for every 2 moles of H2, I need 1 mole of O2, right? This is called stoichiometry. That's the stoichiometry. Being able to go from one thing, H2, to another thing, O2, using your balanced chemical equation. That is a must. You must have a balanced chemical equation in order for this to work. Okay? So now you can see 0.8 divided by 2, 0.4 moles of O2 will react with 0.8 moles of H2. 0.8 moles of H2 to the moles of H2O from the moles of H2. What's the coefficient for H2O? 2. What's the coefficient for H2? 2. So what do I get? I get the same thing, right? Because 2 divided by 2 is just 1, so 0.8 times 1, I get 0.8. Okay? And this is what we call stoichiometry. It's the process of using the ratios of the balanced chemical equation to be able to predict the outcomes of a reaction, or how much of one thing I need to react with another thing. Okay, so let's look at this bottom one. 2 moles of N2. Now I want to figure out first how much H2 is going to react with that. So moles of H2 on top, moles of N2 on the bottom. What is the ratio of H2 to N2? 3 H2s for every 1 N2. So how many moles of H2? 6 moles of H2 are needed to react with 2 moles of N2. Okay? 2 moles of N2. This is N2. Okay, and I want to convert that to moles of NH3 from the moles of N2. What is the ratio? How many NH3s and how many N2s? 2 NH3s, right? 1 N2. So I'm going to get 4 NH3s. Okay? So this is how my chemical equation is going to help me. What if I had started with H2? What if I had said, if I have 0.765 moles of H2, and I wanted to know how many moles of NH3 I could make from 0.765 moles of H2. Here's my balanced equation. Okay. I'm going to get rid of the moles of H2. So how many moles of NH3 are produced in that reaction for how many moles of H2? What's the ratio? Two NH3s for every 3 H2s, right? So I take 0.765, I multiply by 2, and then I divide by 3. What is that? You can do that for me. Okay, so 0.51 moles of NH3. That would have been a lot harder to do, right? This question would have been a lot harder to do because there's no just dividing it in half or multiplying it by 2, or right? It's times 2, then divide by 3. Okay, but I can figure it out easy enough because I know the coefficients. The balanced chemical equation tells me the conversion factor for this. Okay. It's for every 2 NH3s, I need 3 H2s. So I can figure this out. Okay? That's my ratio, 2 over 3. Okay, so we're going to need a balanced chemical equation, convert quantities of known substances into moles, because these chemical equations, they are in mole amounts, right? So I can't, if I have it in grams, to be able to do the stoichiometry, what do I have to do? I have to convert it to moles from the grams. So if you're given the gram quantities, you have to change it to moles because it doesn't work if it's in gram quantities. Okay? And I want to make this very clear. You can never go from the gram quantity of one thing straight to the gram quantity of another thing. So let's say that with N2 plus 3H2 produces 2NH3. Okay? Let's say you had 0.78 grams of H2. You want to know how many grams of NH3 you could produce. Okay? So 0.78 grams of H2 converted to the grams of NH3 from the grams of H2. What is the conversion factor for this? What's that? Yeah, because this is impossible. I would first have to convert using my grams per mole. I can't do this. I can't pull, this is not 2 NH3s for every 3 H2, right? Those are not in gram quantities. This is not grams. That is wrong. I cannot do that, right? So there's no going from the grams of one thing to the grams of another thing in one conversion. You can't do that. You can only convert from one thing to another thing in what units? Moles. That is it. That is the only way you can do it. Okay? So don't try that. I've seen lots of people try it. So that's why I'm telling you right now. Don't try it. It doesn't work. Okay? You cannot do that. Convert the quantities of known substances into moles. You need to convert them to moles. They have to be in moles to do the stoichiometry. You can't do stoichiometry unless it's in moles. Okay? Use coefficients in balanced equation to calculate the number of moles, okay, of the sought quantity. Convert moles of sought quantity into desired units. So what that means is, if I'm going to answer this question, 0.78 grams of H2, first thing I have to do is 78 grams. I have to convert this to moles of H2 from the grams of H2. That I can do because I have a conversion factor right there. 1 gram of H2 for every 1 mole of H2. So this is 0.78 moles of H2. That I'm sorry, 2 grams. Excuse me, you guys, just let me do that. Yeah, go ahead. Okay, 0.78 divided by 2, what is that? This is H2, that's why I had to change it to 2. .39 moles of H2. Okay? Now I can do the stoichiometry because it's in the correct units. Now I can go from the moles of H2 to the moles of NH3 from the moles of H2 using a balanced chemical equation. Okay? So there's 2, 4, 3. So 0.39 times 2 divided by 3. What is that? Well, it should be 0.78 divided by 3. Which is what? 0.26 moles of NH3.
And from there you can convert back to grams.
If that's what they're asking. Now, if they say, what are the moles of NH3, you stop there. If they say, what are the grams of NH3, then yes. Now, because I am in NH3, moles of NH3, I can convert to the grams of NH3 from the moles of NH3. Okay? So nitrogen is 14 plus 3 hydrogens. 17 grams per 1 mole. So 0.26 times 17. How many grams of NH3 are there produced?
4.42.
Say it again.
4.42.
So 0.78 grams of hydrogen will produce, with enough nitrogen, if there's just plenty of nitrogen around, obviously, to react with, okay? Because we weren't even considering the nitrogen, right? But we're just saying there is nitrogen. So 0.26 moles of, 0.78 grams of hydrogen would produce 4.42 grams of NH3. Okay? So if they're looking for the answer in grams, then you go from the moles to the grams. If they're asking for it in moles, you just stop at the moles. Okay? So you just have to pay attention to what they're asking for. But that's the process. That's how I use my balanced chemical equation to predict amounts of product, starting with certain amounts of reactants. Okay? All right, we'll look at this example next time. We'll see you guys.